Right. Hello, everyone. So I'm going to be describing some research work that's still in progress under the coupling approaches for next generation architectures project. This is a Department of Energy project spreading over 4 labs looking at advanced architectures. So as people have noted, there's this parallelism pandemic going on where most of the performance we're seeing on future architectures is coming from parallelism. And that's occurring at all levels in the hierarchy. In addition, they're becoming increasingly hybrid, lots of different device types. So to effectively use these sorts of architectures, you need sort of over 100,000 threads per node and variable workloads. And so far, the sort of treatments people have put forward for this sort of work are either directive-based approaches like OpenMP5 or OpenACC, which has some community use. And then on the C++ side, Cocos has seen a lot of community spread with a portable abstraction layer through template metaprogramming. So that's becoming popular here. And these are getting decent GPU speedups, but it's only treating some of the symptoms. In particular, these are focused more on kind of portability and data motion. One of the difficulties in their system models is, particularly when we're at the strong scaling limits, we just don't have enough work to spread out. So the standard sort of data parallel techniques aren't enough. So we've been trying to explore asynchronous mini task models. So these programming models put together an application through a whole bunch of tasks with clear interfaces, no side effects. And then a lightweight runtime does sort of contact tracing, creates the data dependency graph and schedules work appropriately. So there are a number of these programming models out there: Legion, Winta, HPX. And on the computing side, yeah, as we mentioned, they expose more parallelism because you get not only the data but the task parallelism. But you can also build in things like load balancing, fault tolerant, and mapping hybrid tests to appropriate hardware. On the science side, we can manage complexity by just adding and subtracting tasks from an application. And more importantly, from the Earth system modeling side, we can move away from this sort of large component model of coupling and start coupling processes that need to be coupled and treating the coupled system as a collection of physical processes rather than these large components. And finally, we can include more of the kind of overall scientific workflow, adding things like in situ analysis and stuff. So in Princeton, I think I kind of introduced this, and our project was under proposal review at the time. We've now been funded, so we're about a little over 2 years into the project. It really has 3 components. One is looking at these task parallel systems, and the other 2 are looking at algorithmic improvements in both remapping and time integration, how we integrate forward the coupled system in time. So on the task parallel side, so I mentioned Legion is one of these task parallel runtimes, but we're actually adopting a front end called Flexi, is Flexible Computer Science Interface, that supports a number of these abstractions under the hood, but provides a little bit more application focused abstractions for us to develop the model on. So this framework basically does 2 things. You create a specialization layer according to the meshes you're using. So you can do partitioning and connectivity, separate the owned shared Halo regions, for example. Flexi actually comes with a default one, but it's best to actually create a specific one for your meshes for performance reasons. And then from the task parallel side, basically to make the task parallelism work, you register all the fields with the framework, and then you register the tasks and their interfaces. And as part of those interfaces, you declare which fields are being passed and the intent on those. So either intent in, out, or in Flexi is read-write or read-write. And then the task launching is just a subroutine call to launch each of these tasks. So we've developed a prototype coupler based on this system. We have all the interfaces in the typical coupler functionality for the current sort of style of coupling with large interfaces for each of the large components. And we have interfaces now for all the kind of merging, remapping, and averaging that typically goes on. So this is adequate for sort of looking at the data flows. Some of these functionalities haven't been built out fully, but we wanted to get at least all of the interfaces in so we can start looking at data pathways. So all that's working in Flexi now. We're starting to build out more of the functionality, and then we can start breaking up these large components to see how much more parallelism we can expose. We are waiting for some mesh infrastructure. Flexi was developed for sort of single mesh applications, so any day now we're expecting some new support for multiple meshes. While we're waiting, we've also been kind of developing some of the component models in Flexi as well. So on the ocean side, we've been sort of converting MPasso to a Flexi-based model as an experimental approach. And we now have enough functionality to do things like paraclinic test cases and that sort of thing. We have parallel I/O capabilities, and we're working on in-situ analysis capabilities, both within this project and for adoption within the standard MPasso model as well. Starting with Lagrangian particle tracking as a way to analyze floats and stuff. And this is just one example, the usual sort of point and grunt proof that things are running. There's the data flow graph. This is a simple application, so you don't get as much parallelism as you might in a full application. The land model is a good example of kind of a really multi-process model where this approach might work even better. So we have a group at Oak Ridge exploring extracting capability out of the E3SM land model and developing interface layers for that. They're actually developing layers that support both this Flexi as well as COCOS and other interfaces. So this is just an example of some comparisons where they have some COCOS and other sort of standard MPI hybrid models just to show that the interface is working. And then they have a paper that showed up supercubating there. So that's kind of the summary of where the task parallel works. It's we're still kind of just partway through this conversion, and but we're getting close to realistic enough codes that we can start to evaluate the performance advantages and ease of use for these sorts of approaches. Okay, so now I'm going to switch to algorithms. I won't spend a whole lot of time here on the remapping. These are the RNA-based vaccines. VJ already kind of talked about the Tempest and MOAB efforts, so I won't say much here other than we do support bounds preservation now to try to flatten the curve. VJ also mentioned a couple of new remapping schemes that we're also trying out. One is called weighted least squares, essentially non-oscillatory. And these are basically schemes that can adapt based on properties of the field. So there are online adjustable remaps that look at properties of the field and can adjust the order of interpolation based on those properties. And it's particularly advantageous for fields that change in time and for fields that have strong discontinuities. So we're exploring those. We're also looking at these meshless remap using generalized moving least squares. So meshless is a very useful approach for mapping from different mesh locations. So you don't have to expose just a single mesh. You can actually, for example, interpolate velocities from their native field locations to their native field locations on the target grid. So we support GMLS now with along with global conservation and local bounds preservation as well. So you can build some of these things in to the remap. They can go from low to higher order, 1 through 4 basis degrees. And we have additional property preservation planned, particularly for vector fields, things like divergence free, or what may be more difficult is preserving something like a wind stress curl. But those are sort of what we have planned in the future. So we're doing clinical trials of all these remapping efforts now. DJ mentioned this a little bit, but we're we've got a common framework for testing all of these where we're testing them against metrics like conservation accuracy, extrema preservation, and gradients. This shows some kind of early results. I should mention that the fields we're actually remapping in this framework are based on observed fields, but we've done basically a spherical harmonic truncation of that to provide an analytic representation of those observed fields. So these are examples for total precipitable water and cloud fraction. And you can see the order of schemes changes with whatever metric you're looking at. We're also comparing ESMF as part of that as sort of the placebo part of the trial. So last part I wanted to talk about are some research areas in time integration. As you know, when we couple these models together, we're often kind of lagging fields or averaging fields over a coupling interval. Some of that's to provide more asynchronous runs or for other computational optimizations, and some of it is based on the different timescales in the system. So we've got a few efforts here to look at both new techniques and trying to analyze the numerical implications of the choices that we're making. And to do this, we're having to operate in much more simplified applications. So these are typically combinations of advection diffusion equations with bulk formula, bulk flux formula as the boundary condition. So the first one, so this is a set of advection diffusion equations with a flux condition at the boundary. And we're looking at a scheme on the next slide. This is called a bulk interface flux recovery scheme, where we can actually define the flux as an auxiliary variable, kind of a Lagrangian multiplier approach. And then using Shor complements, we can isolate both the interface degrees of freedom and the flux computation. And we solve for the flux and apply that to the component model. So this gives us flux conservation, guaranteed stability, consistent time discretizations across these. We can maintain decoupled components, that is, they don't have, this approach doesn't have much impact on the coupled component itself. But it's computationally expensive, so you don't get anything for free. So we're working on that aspect of it. So this is just an example of, again, analytic fields kind of testing these coupling schemes across that boundary and showing order of operation. And then we can also see effects like, for example, when you're using explicit or mixing explicit and implicit methods. If you don't use consistent methods, then the error rate goes up dramatically. So there are implications for these, and these simplified approaches can allow us to sort of analyze the implications of those. I think the only thing I really wanted to say here, we're trying to maintain the flexibility of maintaining different coupling intervals and maintaining each individual component model's time discretization. So we're trying to come up with schemes that respect those. So another example of this is a group at Oregon that have been looking at coupled Navier-Stokes, compressible Navier-Stokes. And their simplification came at the boundary, looking at rigid lid. So using this simple configuration, they're testing a variety of implicit, explicit, mixed schemes. So, for example, integrating the ocean forward explicitly and the atmosphere implicitly, but still exchanging horizontal momentum and heat fluxes at every stage. So there are conservative methods here as well, and they show sort of order of convergence here for a variety of kind of low and high order when we've got another approaches in these high mixed methods. So this is another case where we're just exploring these new methods to see what might work. So in addition to sort of trying to introduce new methods, we'd like to analyze current methods as well. So let's go ahead to the next slide, actually. So there are ways of doing both eigenvalue and normal mode analyses of various time integration schemes across the coupled system. And some of the work with sort of simplified interface conditions, stability constraint has been developed that's kind of similar to a CFL condition to analyze stability of a coupled time integration scheme. So this is described in a couple of papers shown below. But what we've done, if we go to the next slide, is use that simplified kind of stability constraint and explore how often maybe in a real coupled system we're exceeding that constraint. So you can analyze the data in E3SM and look for areas where that particular criterion becomes unstable. It doesn't necessarily mean that we're actually running an unstable simulation here. It's because that was based on a simplified configuration, but it gives you some idea kind of how close we are to stability limits in kind of typical time integration schemes. And what you see here is that you can have potential instability, particularly in regions where there's small diffusivity across that interface and a large coupling coefficient. And then the next slide. This sort of demonstrates on a component basis that these can be vary seasonally as well as on the ocean side, for example, due to individual events, so they can be sporadic and time dependent. So this is just some examples of the kind of analysis we're trying to carry out, trying to do more formal analysis of time stepping schemes in coupled simulations. So that's kind of a summary of a lot of research effort that's going on. It was kind of a quick pass through, so I'm happy to entertain questions.